Bienvenidos. At this point, we have learned all of the different rules for differentiating different families and combinations and compositions of functions. And so our next unit is on applications of taking derivatives. We want to look at different ways that being able to take derivatives will help us in different areas. Now, we know that the derivative can be interpreted as the instantaneous rate of change as a function. And what we're going to look at today is something called related rates, which is where there are different quantities that are changing at different rates, but the rates of change are related. Now, I've got an example for you. Here we have a spherical balloon, and if someone were pumping air into this balloon, then the volume, the surface area, the circumference, and the radius, all of these quantities would be increasing, but they'd be increasing at different rates, but they're all related to each other. There's a relation between the rates at which they're increasing. And what we can do in a situation like this is use implicit differentiation to see how these rates are related. Now, I just want to jump straight into an example so we can see how this works. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So we're told that the volume is increasing at a rate of 100 cubic centimeters per second. That is a constant rate, and that's basically the rate that the air is moving into the balloon. So we've got some sort of a hose maybe that is blowing up this balloon, and the volume is increasing at a constant rate. What we want to know is how fast is the radius increasing, and we want to know that at a specific moment of time when the diameter is 50 centimeters. Now, the volume is increasing at a constant rate, but the radius is not going to be increasing at a constant rate. If we think about how we blow up a balloon, usually it starts to grow very quickly for the first few seconds. The radius grows very fast because it doesn't take too much air to increase the radius at first. But as you continue to blow up a balloon, as it gets bigger and bigger, the radius starts to increase at a slower pace because when it's bigger, it takes more air to grow the radius. So it's a little bit complicated here. It's not just going to be both of them change at a constant rate. Anyways, I just wanted to give a little bit of a context so that we can think about how things are changing here before talking about how we solve it. So what we want to do is we're dealing with the volume and the radius, and we need to think about how these quantities are related to each other. And there is a formula for the volume of a sphere as a function of the radius. I don't know if you know that formula, but it is V equals 4/3 pi r cubed. That is the formula for the volume of a sphere as a function of the radius. Now, both of these are actually functions of time. The volume and the radius are changing based on how much time we've been pumping air into this balloon. These are both functions of time, and so what we can do is we can differentiate both sides of this with respect to time. So we've got d over dt of v equals d over dt of 4/3 pi r cubed. And we're remembering that volume and radius are both functions of time. So when we differentiate the left, the derivative of v with respect to t is just dv dt. Right? That's how we write the derivative of volume with respect to time. Now, on the right-hand side, we've got 4/3 pi is just a constant multiplier. So we can leave that out front, 4/3 pi. And then we have to multiply that by the derivative of r cubed. Well, the derivative of r cubed is 3r squared. but we have to multiply by dr over dt. We've got to use the chain rule here because r is a function of t. The radius is a function of time. So when we differentiate r cubed, that's 3r squared, but times the derivative of the radius with respect to time. Now the 3's are going to cancel on the right-hand side. We can simplify that a little bit. dv over dt equals 4 pi r squared times dr over dt. And I want to make a quick comment here. The reason I'm writing out dv over dt instead of just v prime is that we have to remember that volume is both a function of time, but it's also a function of the radius, right? If we're thinking about the formula for volume, we could look at it either way. And so putting v prime doesn't tell us if we're differentiating that with respect to the radius or with respect to time. So it's important that we use this notation so that we're certain what we're differentiating with respect to. Now, we started with an equation that related volume and radius, but when we use implicit differentiation, we now have an equation that relates the rate of change of the volume and the rate of change of the radius. There's also still the radius in there, so this relationship depends on what the radius is at any given moment. But now that we've used implicit differentiation, we can actually have a relationship between these two rates, and we can figure out what we need to. What we want to find is how fast the radius is increasing. So that's dr over dt, specifically at the moment when the diameter is 50 centimeters. Now, really quick, we're told the diameter is 50 centimeters, but we don't have the diameter here anywhere. We have the radius. So remember, the radius is half the diameter, so that means r is 25. And so we can actually plug that in, right? We need dr over dt, but we know what r is at this moment. We also know dv over dt. It's a constant. We're told that that's 100. So we can plug those in and solve for the unknown. So we've got 100 equals 4 pi times the radius squared. So that's going to be 25 squared. And that's times dr over dt. Now, I'm not actually going to square 25 because that's more than we need to do. I'm going to write this as 25 times 25. And the reason I'm doing that is because on the right-hand side, 4 times 25 is 100. And we also have 100 on the left-hand side. So if we divide both sides by 100, it's basically going to cancel those out. On the left, we're going to be left with 1, right? Because 100 is 1 times 100, or when we divide 100 by 100, we're left with 1. And so if we want to get dr over dt alone, we still have this 25 pi on the right-hand side that we need to divide by. And if we divide both sides by that, we've got 1 over 25 pi equals dr over dt. And if we want a decimal approximation, we can plug that into a calculator, and we get 0.0127. Now, this is the rate of change of the radius. The radius is measured in centimeters, and because we're changing with respect to time, and time is measured in seconds here, this is going to be centimeters per second. So at the moment when the diameter is 50 centimeters, the radius is going to be increasing at a rate of 0.0127 centimeters per second. Now, before I leave you with some more example problems to look at, I want to talk about the steps that we take in general in these problems to figure out whatever unknown rate it is that we want to figure out. So the first thing that we had to do was we needed to identify an equation that related the given quantities. So let's write that out. All right, so first we identify the equation that relates the given quantities. And then once we had that equation, what we needed to do was differentiate implicitly and that gave us a relationship between the different rates. So I'm going to write that as differentiate implicitly with respect to time. And then once we've done that, once we had that, we could plug in the given information to solve for the unknown. Okay. And the thing that's important to understand is that we cannot make these substitutions until after we've gone through the process of differentiating. The reason that's important is because one of the pieces of information we had, which was the diameter, which also gave us the radius, that is not something that's always true. It's not true that the radius is always 25. The radius is changing as a function of time, and we were only looking at that moment in the very end when we wanted to figure out the final answer. If we had plugged in 25 earlier, if we had plugged it into the original equation, we would have had the volume being constant. But that's not true. It's not true that the radius is always 25. The radius isn't a constant. It's just at the moment that we're looking at, the radius happens to be 25. So once we're ready to plug things in at the very end, that's when we can substitute in our values. All right, I have some example problems for you to look at, and the next class is going to go through more example problems. We really want to get a wide variety of experience here because every problem has a different relationship, and every relationship has a different formula or equation, and we want to look at a few different things from geometry and other topics. And so each one of these is going to take a bit of time. We have to identify the relationship, we have to go through the differentiation process, and then plug things in. So really, each of these examples is going to take some time, so make sure you go through several of them to get a good idea of the variety of things where this is useful.